So, ready, go? So today we are going to talk about how to specify a design. So people think that the difficult part of a design is to do the design, but actually the most difficult part is to say what you want and what the design is supposed to do. And in fact, when you do a design, then at the end, when you are done, then the question is, did I really implement what I had in mind in the first place? And so this is also true when you are a company. You know that the way in which companies work is that there is what is called a supply chain, meaning that there is a company, say a car company, then the subsystems that he is putting into his car come from other companies. And so what happens is that they buy equipment, or they ask the companies to design equipment for them. Now the question is that when there is a long contract that specifies what the other company is supposed to do. Now, if you forget about something that you want the supplier to do for you, then it does something, it delivers it to you, you put it in your car, and the car doesn't work. And then you go to the supplier and say, you turkey, you did a horrible job, so I'm going to sue you and I'm going to strip you to death. And the guy say, no, I did what you told me to do. Then they look at the contract and say, oops, forgot, right? And so it's not only an issue of technical issue, but it's also a real issue that involves hundreds of millions of dollars. So the specification of a design is a key point. So you have really to be very precise about what you want. And this is true across company boundaries, but even inside a large company, you have divisions. And so it's not the same group of people that does the entire design. You have the people who do the architecture of the design, and they deliver specification to their other divisions that often work in parallel. So it's extremely important that everybody has clear in mind what they're supposed to do. Okay, so one thing is that if you go to industry and you say, okay, what is your specification method? So, well, people use Excel spreadsheet. I'm not kidding. So they use Excel spreadsheet, or at most Word statement. Word meaning Microsoft Word statement, right? And then they have programs that help them to organize these statements that they talk about. And that is a very famous program that is around. It's called Doors, and it was developed by a company called Telelogic, a Swedish company that was acquired by IBM. So that is the standard. So everybody plus his brother uses Doors. But Doors is a glorified management system for Word documents. I mean, so at some point when you analyze this document, so one thing is that at least you know where they are. And at least you know that if you change something, you got to change something else. Okay? So this structural situation is taken care of. But what is inside these statements, the meaning of these statements, is not clear. It's English, right? So, yeah, you say English is pretty clear. Well, up to a point. When you specify, for example, this thing has to go fast. Okay, define fast, right? I can make something fast. With respect to what? If the comparison is a snail, then fast is not exactly the same as if you specify with respect to a cheetah, right? It's not. So the point is that you have to be precise, and you have to say what you mean in the most precise terms, so that there is no argument, right? So you know what you have to do. Not only, but then you can verify against those statements, because being expressed, hopefully, in a mathematical term, then you can run simulation, tests, whatever you want, see what comes out, and then compare against the specification. And so you can say, yes, I made it. No, I haven't made it. So I need to change my design. Okay? So this is an extremely important part of any design. In all your career, remember my words. If you don't follow them, sooner rather than later, you will be dead. Believe me. Not literally, but that means you are going to be in real tough situations. So always try to be as precise as possible and put down things that can be measured. Because if they cannot be measured, how the heck are you going to claim that your design is correct or not, and that you have done what you're supposed to be? Oops. Okay. So, when a design is correct. A design is correct when it meets a specification, as we said, obvious. A design without specification cannot be right or wrong because you don't have a comparison, right, to run again. And so simply running a few tests and then looking at what happens and say, this looks pretty cool. That ain't going to work, right? So that is the reason why in the specification of your project it says, column, thou shall verify your design before implementing it, right? Which implies that when you define your project on the platform that we gave you, you better tell me what are the properties of this application. Otherwise, you are going to be, the first time, you are going to be in serious trouble to pass the class, okay? So it's not as scary as when it will happen to you next when you go and work, but, that's okay. So many embedded systems are deployed in what is called safety-critical systems. So, for example, cars are safety-critical system. Of course, airplanes, safety-critical system. Things that deal with health are safety-critical. So you know that now one of the largest growing company is the company that makes the Da Vinci robot. What is the Da Vinci robot? It's the guy that cuts you up, right? It's for operations. These robots are so precise that no human can replicate the precision which they can cut you up. Not very, good example if you like, because then you say, how was Da Vinci designed? So you hope it is being designed correctly with formal methods and all of that, because it's going to cut you up. And so it better be good, right? Better not have bugs, right? So that is the issue about security here. Safety. So the challenge of dependable software, of course, is that, as we said before, devices that are monitoring your vital signs as well as doing something to you are built with electronics. And so electronics are consisting of software and hardware, and you hope that the hardware is not going to break and the software is not going to have bugs, right? So that is the thing. So horrible here, the patient collapsed while walking towards the cashier after refueling his car. A week later, the patient complained to his physician about an increasing feeling of unwell being since before. And so that is actually a software defect of the pacemaker, right? Not good at all. And it was discovered later that defect was triggered by the electrical field that you have in gas pumps, right? So not good. So every time you go buy a gas pump, you feel, your pacemaker goes bananas. Not very good. Okay, so all right. So this is a kind of situations that happen. And indeed, there is also a very interesting phenomenon, and this is due to actually the modeling of your heart. Because if you want to do a pacemaker, you've got to have a model inside the pacemaker itself of what your heart's supposed to do. And then there are sensors that are sensing if the heartbeat is going up, down, and stabilizing, and all of that. So if you have a wrong model, and you're trying to stabilize your heartbeat, instead of stabilizing it, it goes all over the place, right? So that is actually has happened a number of times. So you got to be extremely careful there. So now, what is the specification? Well, specification is a mathematical statement of a design objective. Now, notice that I put a mathematical statement about design object, meaning that we want to be very precise about what specifying a design is. Now, a verification problem then is to check if your design satisfies the mathematical formulas that you have used to establish what the property should be. Now, the controller synthesis is another kind of topic that is connected to it, albeit is part of the design itself. Now, wouldn't it be nice that the design process is guaranteed always that is doing what you specify? Now, what will be best if I give you the specification and then there is a wonderful algorithm that take this specification and build the system so that the specifications are correct by construction? Hallelujah, no heart attacks, no nothing. Hey, we have it, right? And that is the problem of controller synthesis. So you're given an incomplete design, you're given a specification, and then get a way, either by hand, but hopefully better by computer program, that implements a control loop that makes your device act as you specify. Okay. So remember we talk about model-based design, in which you start from a model and then you derive the rest of the design in a particular sequence. So in here you have a model and you have requirements, and it will be nice to synthesize from the requirement the correct controller so that the model does what it's supposed to do. So I gave you the example of a pacemaker. That is a controller. It's controlling the rhythm of your heartbeat, right? So it's giving the reference, right? So that is the controller, and the model is the model that you have of your heart. And so you want to build a closed-loop control so that the system consisting of the heart plus the controller does what is a sane heart supposed to be, a healthy heart is supposed to be, right? Now, of course, when you are in design time, what you would really like to do is to verify that the requirements are satisfied on this closed-loop system. And we already said that there may be automatic way actually to get away from verification problem because you do it correct by construction. It's called controller synthesis. Or you want to be able to run a computer program that tells you whatever you have done up there in the design phase is actually satisfying your requirements. So among which, for example, there are different strategies. One of these strategies is what almost everyone uses, which is simulation. Now, would you trust, for example, if I tell you run 5 minutes of simulation of a pacemaker, would you be satisfied to implant your pacemaker in your heart? And I say, everybody knows. You get it, right? Why is that? Because you want to be reasonably sure that under all possible circumstances, your thing is doing the right thing, right? Now, with simulation, can't do that, right? So simulation is essentially like a virtual test bench in which you put some input, you see what the outputs are. And so the quality of your verification depends on how good you are in identifying the test cases. Now, there are formal ways of defining test cases in such a way that you visit the space with a certain density, the space of possible occurrences, but you're never sure. So people then are very interested in doing what is called formal verification, which is, again, an automatic way of looking at all possible cases, right? Okay. So we need a formal way to write models and requirements so that an algorithm can process it, and that's formal verification. Code, right, that you can buy or, but the state of the art is not so good, meaning that you can formally verify designs, but the complexity of design that you can look at is limited. And so that's the reason why I told you about the methodology. So if you can break down the methodology into sub-steps and every step is reasonably small, then you can apply this method. If you do flat, right, so you give entire implemented design where every transistor has been implemented, and you have a specification all the way here, there is no hope whatsoever of being able to verify automatically that this implementation of your design satisfies the requirement. So you have to play, given the fact that the problem is mathematically very complex, you always have to play the game of restricting the space in which you operate the verification. Okay. So, talking about this, when you think about your design and you think about what you would like to assert, is one assertion is that suppose that I can identify, actually they can, bad states in which your heart should never go because of fibrillation, for example. If you fibrillate, not so good, right? So the point is that you want to make sure that no matter what happens, for example, your heart is never going to be in the fibrillation state, right? And so how do you express that property, right? You want to say that no matter which trace, right, which sequences of state your system goes, you are never going to touch that particular bad state. Now, this one is also called a safety property. So you want to be safe. Never touch the bad state. Okay? So now, if you look at this, it says that no matter what the evolution of the system is, you never touch the bad state. Which implies that you have in mind the fact that the system evolves, right? So there is time involved, or in reaction index, or whatever you want to call it. So there is evolution of your system. And your properties have to be expressed in terms of the evolution. So are not static properties. Say, oh, this state has to be good. No, you want to say that for all possible evolutions of your state, you never touch the bad state. Okay? So that's the reason why we need temporal logic. So logic is in general a language that we use to express properties in Boolean terms. So in fact, the property is either true or false. So it's natural to think about the Boolean space to express properties, but you want to have a way, and we know that, for example, propositions or propositional calculus, or what you want to do, is static. So it's not talking about evolutions, right? And so the point is, how can I make assertions in a formal way that talks about evolution in time, right? And this is what temporal logic is all about. Now, I'm going to post the original papers by Amir Pnueli, who was a computer scientist from Israel, but then at the end of his career went to New York University. He was a real quote-unquote genius in the sense that he was very good at logic and mathematics and all of that, but he had a keen understanding what needed to be done to solve some of the problems that we are meeting in designs. So in fact, in 1977, he proposed this temporal logic as a way of asserting properties of a design. He ended up eventually winning the Turing Award, which is like Nobel Prize of Computer Science, for this discovery, for this idea of using this logic. Okay. So now let's look at one example of this. We already said the heart. The heart is, in my opinion, is a very good example, right? And I express you what a property could be. Another property about the heart is that you want the heart eventually to go to a steady state, so a regular beat, right? And so there is another temporal property you want to say. I never want to go into fibrillation, but eventually I want to go into the good rhythm. So I start bad, the controller kicks in, I get the impulses given by the pacemaker, and then my heart is going to settle down to normal operation, right? So that, would you express that? You want to say that eventually, so at the end of a trajectory, you are going to be in the state that you desire to be. The previous one, I said you don't want to be in the bad state. In this particular case, I say eventually you want to be in a good state. Okay, so these are essential to insights that Pnueli had. It's like we need these two basic constructs: eventually and always don't touch the bad state. Right. So these two constitute the basis for building temporal logic. Okay. So this is another example. Is a space-wire protocol. Is a European Space Agency standard, and it's all about what happens if you detect an error, right? So something goes wrong. And then in general, what do you do when you can't work with your computer, blue screen, and it keeps on blue screen and all that? What do you do? Reset, but that may not even work, right? So what do you do? There is the ultimate reset. When you take out the battery, right? That's the last resort, right? If you take out the battery, put it back, still a problem, you're hosed, right? But in general, that is the ultimate reset. What does that do? Now, what does, for example, powering the thing off, right, and restarting, or better yet, taking the battery out? Why? Because everything is, right, gone. And you have to leave it there for, say, 30 seconds. Why do you have to leave? For example, when you go and call the cable company, they say, oh, it doesn't work. Say, take out the modem, unplug the modem, classical, and then leave it there for at least 30 seconds. Why 30 seconds? Any wild idea why you have to keep the thing there quiet for some seconds? So for the capacitor to discharge, the capacitors are keeping the circuit alive, right? For example, I don't know if you ever heard of a supercapacitor, right? The supercapacitor are these humongous structures that are used to store energy, right? So capacitor is storing energy. Now, of course, it loses energy through leakage and all of that. But in principle, if you put voltage across a capacitor, there is an accumulation of charge that stays there forever, right? So now we leave it there 30 seconds because then there is a discharge that occurs because of the resistances. If there were no resistances, it wouldn't work and would be hosed anyway. Okay? So a 30 second is because of that. So don't doom because it's not going to work. It's not really going to reset. Okay, so reset is important. Now, designers always think if someone wants to reset his system, you know that, for example, you have to put there is a reset button, you have to aim it with a paper clip and all of that. Now, what does that do, in your opinion? Not so much the initial state, let's see. Exactly, but what property does that node have to have? Yes, so it has to be known, right? So the reset state is something that we know about, right? Because many of the problems that we didn't do a formal verification. We ended up in a bad state. And one classical thing of a bad state is that I don't know where I am. I have no information. So if I want to do something, I have to be sure that I'm in that particular state. So the reset state characteristic is that I know what it is, right? And so that is true is the initial state, but is the ultimate initial state because I know what it is, right? So I know that I can restart from that because I know where I am, okay? This is what it does, right? So essentially the thing says, well, if something bad happens, go to the reset state, and then until the reset signal doesn't disappear, stay there. When the reset state disappears, you go to a state which is called wait error. So you wait for the real input to come in and to restart the operation. Okay, and it's a protocol, right? It tells you what to do, what sequence of things you got to do. And so if you look at at this specification, so this is a specification. It tells you which sequence of things must happen, how long you have to wait in a particular state, and what is the next state after you have been in that reset error state, right? So all of this imply that you have to give the name of a state, you have to give the property that you want that state to have, and you want also to tell something about the evolution from that state on. So it's a classical case in which you need temporal logic. Now, this one is another good one since you had to fight with it, right? So in your iRobot exercise, right? Because what it says is that you have a starting position of a robot, and then you have a bunch of obstacles. In your case, it was actually falling down from the ramp, right? And then you want to say that you want to get to your final state, and if I remember correctly, your exercise was to march up and then march down from the ramp and go back to the initial state, right? So in this particular case, the initial and final states are the same. It didn't matter what the trajectory was as long as you didn't fall, right? So is this a safety property only? So would you be able to specify what the system has to do just by indicating the bad state or no? Well, for sure the bad state, right? You don't want to fall down the ramp, right? So that's the bad state, off the ramp. So that's a property, never off the ramp. Is that enough? No. What is missing? You need to come back, right? And so eventually, do I tell you a bound? No, I say as long as it can be 200 years, hopefully not. But, in principle, 200 years will be correct. You can put a timer, but the key point is that eventually you want to be back to the initial state, right? So you see the two propositions, same thing here, right? So you have to avoid the obstacles, and then eventually you have to be in the state phi, right? And for your exercise in your class, you have to do it. Now, it will be interesting, and I think you will see in your next lab some tool in which you can do things, but try to write down this condition, as we just said, in mathematical terms, and try to verify with the simulation if its properties are true or not. In principle, you could also synthesize a controller that does that, right? That is for advanced graduate students. Okay, so the undergraduate don't panic. Okay, so suppose that there are end destination, then of course the robot, you may want to say that I'm going to visit all these destinations in sequence, right? And that's another proposition that I need to state, which is related to the evolution. So I want to go through phi 1, then phi 2, then phi 3, then phi 4, then phi 5, whatever, okay? Good. And it's more complicated, of course, than phi, but from a mathematical point of view, ain't that more complicated. Now, okay, so we said all of this, and so we have to start building this logic. So logic, if any one of you has done any whatsoever little class of logic, you know that the first thing you got to say are the atomic formulas. So it's where you start building everything, right? So because in general, logic or a computer language or anything of that sort, you have to start from the basic clauses, right? The basic things upon which you build the edifice that you want to build. Now, the point is that, for example, also in mathematics, pure mathematics, right? These are called the assertions, right? That's where you start from. The postulate that you cannot prove because you don't have anything to prove against, right? So these are facts, right? So these are the formula. So the meaning, for example, if I write x and x is a pure signal, writing x in the formula means x is present. Remember that x is present is different from the value of x, right? I can have x which is from 0 to 500, right? But the fact that x is there or is not there is a logic proposition. I'm here, I'm not here. The other one is a numeric proposition. Okay? Okay. Now, x equal to 1 means that x is present and has value of 1. Okay, this one from 500. Okay. Now, S means that machine is in state S. So these are propositions, basic proposition. The value is true or false, because that proposition are in the logical space. And so 0, 1. Okay. Propositional logic. So propositional logic formulas. So at this point, I have to build upon this basic stuff, right, that we said before. Now, how do I build? I have to define operations on the basic stuff to get another stuff that belongs to the space of the good stuff, right? And so in the logic, you have to define these operations. Now, the operations that we have here is and, or, implies, and not. Okay, so what is or? Or means P1 or P2 is true, right? And so which means that P1 is true and P2 is false. The formula is true. P1 and P2, both of them have to be true for the formula to be true. Then you have P1 implies P2. Now, this is start getting more interesting, right? P1 implies P2 means if P1 is true, then P2 has to be true. This is the formula. So may true or false, by the way. So you have your system, and the system goes, and P1 occurs. Then if P2 is true, then the formula is true. Okay? So that doesn't have to be 0, 1, or all that. It is a logical statement. So if P2 is true after P1 is true, then you say that the formula is satisfied for that P1 and P2. Now, not P1 is true if P1 is false, we all know. And so the P1 and P2 that we put there are either the facts that we had before or one of these formulas. So I can have a composition. So I can have P1 and, open parenthesis, P1 or P2. Actually, let's put P3 or P2, otherwise it's inconsistent. Okay? So that's the fact that I can build as many formulas as I like using the basic operations and the data. Now, question. So if P1 is false, what does the expression P1 implies P2 evaluate to? Right, but let's see. Who has, so he says true. Other opinions? And why is true? Say it again.
True or false.
In some sense, yes. I mean, you have, the point is that I'm not saying anything about P1 being false, right? In some sense, when I say this. But actually, the point is, since I don't say what it is when P1 is false, it's true. Because it's a statement, right? So if I don't say anything, it evaluates to true. It's really a don't care between you and me. But by, I have to say, convention, we say it's evaluates. Also, there is another way in which you can state P1 implies P2, in which you immediately see that. It is called the contraposition. So can anyone tell me what is a contraposition corresponding to P1 implies P2, which is the negation of this? Right? Well, you can write it down in terms of P1 is always 2 or something else happens. Or you can, yes. Perfect. Not P2 implies not P1. Okay? And so, of course, that formula evaluates to true, right? In the case of P1 is false, right? So, here you go. Execution trace of a state machine. So, we know execution trace, is a sequence of states, input and outputs, right? So, is in some sense a recording. I always like to think about it as a black box of the execution of a finite state machine, right? The black box is the thing that records everything happened to your plane when it goes down, and you pick up the black box and figure out what happened, right? So this is a black box, right? The execution trace is what is in the black box of the evolution of the finite state machine. Now, as we said, temporal logic is reasoning about evolution. So what do you have to reason about? You have to reason about traces, right? So sequences of states, input and outputs. Okay, so the propositional logic on traces starts with an axiom again, that if a property P holds for a trace, then it must hold for an initial state, and if it holds for an initial state, it must hold for every state in the... And this is by definition. We say that P holds if and only if this is true, okay? So it's not that it happens, right? It's by definition. So we say that, for example, if you have a proposition that is valid in Q0 but not in Q1, then the logic formula P does not hold for the trace. Okay? So it's to be true for everything. Yes? No. Because there's a definition, right? Induction you build. That's what I want to be very clear about, right? There is no reason why you could say, if this proposition is true at the initial state, must be true for all the... There is no... Maybe not, right? But then the fact that we say that this proposition holds for the trace implies that it's always true. Okay? So it's a definition. Okay? We are not to the induction yet. Okay? All right. It's odd, but you have to start from somewhere. It's like the initial step of the induction. Okay. Now, what kind of formulas do I have? So P means that P holds in Q0. Aha! And now we come to the interesting operators. Now, these operators that are G and F and so on, and X and U, are not belonging to the standard logic, right? And that's where the temporal aspect comes into play. So the G means that global is a globally true operator, which means that for every traces that I have, this must be true. Okay? The formula phi must be true. And that's the reason why we say globally. So, for example, how would you state the safety property? So suppose that phi represents the set of bad state. And I want to say that no matter what the evolution of my system is, I never go into the set phi. How would you express it with a G operator? It's a bit too much, right? So I wanted something very compact. It is what you say, but you have to compactify. So how would you compactify? Any wild guess, any recommendation how would I say? So globally is true, right? So I have to use global, right? And I say I don't want to be in the state phi. So? Right, globally not phi. Right? So which means that no matter where I am, no matter which sequences I am in, I'm never going to be in the set phi. So globally, not phi. Okay, so which is what you said, but instead of saying this or that or that or that, just say not phi. Right? Because globally not phi means for everything, never phi. Right? So it's a yeah. Which is essentially, I mean, the intuition is what you say, but it's the way of saying it. Yes, because phi is a proposition, and globally not phi means that for all states. Right? Okay, so now f of phi. Okay, f of phi. F. What does it mean? Future. F stands for future. So mnemonics. G globally, F future. So now, what is the meaning of that? That in the future, I want to be in some good state. Right? Something good must happen. Eventually. So it may not be true at the beginning, but I'm going to be there. So this is the pacemaker, right? So eventually I want to be in the good state for my heart. I didn't start that way, and all the controls for some number of steps may go bananas still, but in the end I want to have the pace that is supposed to have. I would use the F operator. So that is true if for every trajectory, eventually that statement holds, and from there on, right? So there is a time in which the thing is true, and then from there on it always holds, and that is F. Now, X of phi. X of phi implies the next state operator. So I'm in QK, right? I'm in particular state, right? And if I say X phi, it means that if the next state, so I take a transition, I'm sitting here, the proposition must be true. Okay? Now then, phi 1, U, phi 2, that's an interesting proposition as well. By the way, I'm used to say phi because that's the way the Greek people pronounce it. Right? Unfortunately, I did classics, so this is the way in which the ancient Greeks pronounce it, right? But in America, I say phi, right? Which kind of, okay. So I can't get myself to say phi. And so forgive me, but it's the same thing, okay? It's that funny letter, okay? So when we say phi until phi 2, phi 1 until phi 2, what does that matter? So if you start thinking about it, until, right? Phi 1 until phi 2. So it means that for a certain number of steps, phi 1 is true until another proposition becomes true, and then I don't care about what phi 1 does. It can be always true, it can be always false. I don't give a damn. Okay, so this is phi 1 until phi 2. Okay, I got into that situation. Okay, I'm cool, no matter what phi 1 does. So, for example, this one again, talking about the pacemaker, phi 1 could be don't die, don't go into the fibrillation state, until you are in the good state, so you don't need anymore to check for fibrillation. Okay? So phi 1 is certainly true. Maybe false, but doesn't matter because I am in the good state. Anyway, so, okay. So this is the use of phi 1 until phi 2. Now, there is an interesting point that are all of these statements, or these operators necessary, or can I express some of these statements as a function of some others? So in other words, what is a minimum set of operators that I can use to express everything? This one is redundant, by the way. So there is a short, well, I'll let you think about it and come up. I think it's in the book, by the way. So, but if you think about it, what will be the minimum set of statements that I need to express everything that I put down there? But you have it because it's convenient, right? Notation has two meanings. One is to, of course, to describe what you want to do, but the other one is to be concise about it. A notation helps people to reason about things, right? So the more concise it is, the better it is. So maybe that one of these operators, actually, as I said, it is true, can be built as a sequence of other operators, but makes my life more complicated. I just use one letter and I'm done, right? And so it is good to have all of this. So P is a proposition, G means globally, F means finally, future, eventually, X next state, and until, U is until. Okay, so we said already, we gave examples. And that's it. So this is what is a linear temporal logic. Okay, so it's called linear temporal logic. Now, is this all we can do? No. There are certain things that I want to say that I can't say in linear temporal logic. And so people went bananas. After Amir Pnueli started talking about temporal logic, then people invented computational tree logic, and then people invented computational tree logic star, and then all kind of logic, and they say probabilistic temporal logic, and PTL, and so on. So everybody's invented a new temporal logic concept. And why is that? Because it's not universal. So there are properties that I cannot talk about, right? And so the issue is that I have to enlarge the space of the logic language that I'm going to use. Now, as we all know, the more general you are, the more host you are. Meaning that to verify if a particular system satisfies that formula may be relatively easy or incredibly difficult. So many of these logics are undecidable, which means I never know if it's true or not, right? So I cannot have a guarantee that if I'm applying my rules and all of that, and the answer is maybe, right? Because I didn't get a counterexample. So does that mean it's true? I don't know. I have to keep on going. For how long? I don't know. Undecidable. Okay, this is the meaning of undecidable. Okay, so for example, the basic model of a computer, which is a Turing machine, to answer the question, is my Turing machine going to halt eventually, is undecidable. I mean, we're talking about really bad stuff. So everything that you do in computers is bugged by that original stuff, right? Everything that you can claim about the way in which your computer operates, unless you restrict the space, is undecidable. So maybe, maybe not, right? And so that's the reason why you get the blue screen. Maybe, maybe not. Not. Okay, so, all right. So G, we already talked about what it means globally. So if you have a trace Q0, Q1, Q2, Q3, globally true means that for that sequence must be true, but also the sequence Q1, Q2, Q3 has to be true, and also Q3, Q4, Q5, and so on. So all the sequences that you can build, the tail of the sequence that you can build has to be true, right? Now, the globally then is that it must be true for all the for every suffix of the traces. So if it holds for Q0, it must hold for all the sequences that you can build, all the traces, right, of that system. Okay, so for the LTL formula, GP holds for a trace if and only if P holds for every suffix of a trace. So this is related to the fact that we have talked about LTL only for one trace, right? Because the linear temporal logic is defined on traces. Now, when we want to assert that my machine a machine, not anymore a trace, a machine satisfy phi, right? Globally satisfy phi means that for any trace that is true, right? For all of them, right? For all of them. Okay, so that's the way in which we assert properties about a system. We say for every trajectory of that system, we know that this property is true, so it is shorthand is true for the entire machine. So this we already said, and so on. So this, and indeed, when something is globally true for any sequence in the damn machine, then we say it is an invariant. So it doesn't change. It's always true. Right? It's an invariant. And by the way, the invariants, I don't know how many of you have done ever or read papers about proving properties of programs. The way in which you do that is by proving that invariants hold, right? So, and that was the first time that this nomenclature of invariant came about. F, we said before, eventually, finally. So it means that the LTL formula FP holds for a trace, Q0, Q0, if and only if P holds for some suffix of the trace. Okay. Now, by the way, this small between you and me, I never like a definition stated as if and only if, because if and only if is a necessary and sufficient condition, right? So I would really very much like you, instead of using this notation that unfortunately many people use, so this one, I have not written this particular piece of slide, but don't say that. You say, by definition, this is true, okay? Not if and only if. It's the same thing, logically, but not, it's not, right? Because it says that you don't have to prove it. It's a definition, right? So if I say, my, for example, I can say a sequence of calculation, the fixed point theorem, for example. It says that if you put x0 into f and then you get x1, you put x1 into f and you get x2 and so on and so forth. It's a fixed point calculation. So you keep on putting the results of applying f into f, right? Then we say that if a certain particular condition on x, on the sequence of x's, then you know that this is going to converge, right? So you're going to get x equal to f of x eventually. So you put something here, comes back identical, right? That's a fixed point. So there are conditions under which this is true. Now, that is a sufficient condition. A sufficient condition, for example, is f is a map of a unit circle onto itself. That is a sufficient condition, which implies that I may have another function that admits a fixed point that is not from the unit circle to itself, but I cannot say, right? So the difference between necessary and sufficient condition and sufficient condition is that necessary sufficient condition tells you that if this thing is true, then this thing converges, but if the computation converges, means that the property is satisfied, if and only if. But you have to prove this, right? It's not. Instead, if I say my system is safe if I never get into a bad state, that is a definition. I don't need to prove it. It's a definition of what it means a system is safe, right? So don't confuse the two, please. Please, please, please. Okay, so it's a very different statement. So this one is not really if and only if, is the definition. By definition, this is true. Okay. Now, what it means. So if the LTL formula, so suppose at some point the formula phi2 is true at Q2, okay? Then from Q2 on is always true. So that's the meaning of the formula. Now, yes?
The previous slide, when you said that from Q2 it will always be true, right? So
Yeah, globally.
in that, in the
Okay. The future one, yeah.
Now, shouldn't this be hold even in Q3? Because it will be
Should also for Q3, absolutely. Now, there is another form of the future that means it has to happen infinitely often. So in other words, it's true at this point, and then it may become false, is false, and then it becomes true again, then false, it becomes true again, right? Okay, so this, for example, when you want to say, suppose that you have I don't know, when you race, right? So, for example, when you do a cross-country race, right? Then you must go through the correct. So it must be true that you go through the exact points, right? In between you can do whatever, but you have to go through this, right? Same thing as skiing, right? So you have to go through this. Now, in between you can do whatever you want, but you have to go through this, right? So that will be this repetition, right? But it doesn't have to be true for all states. Now, in here, in this operator, and from then on, it's to be true. Now, proposition, this is another interesting thing, is that, of course, LTL proposition can apply to other LTL propositions, so it can have a nested situation. And so here you have G, so globally, must be true that if that X implies eventually Y. Okay, which means that every time you hit X, you sometimes in the future have y, and this statement has to be true for all possible traces. Okay, that's globally, Okay, so I can nest any formula that I want, because that's the way in which we build the logic. So globally, if at any point in time x occurs, then it is eventually followed by y. So this evaluate to 1 if these conditions are satisfied. So evaluate to true, I shouldn't say 1, to true. Now, every input x is eventually followed by an output y. So this one is what we said before. Now let's look at what happens in the state. So x holds, and then we got q1, right? So if and only if it holds for any suffix of a trace, blah, blah. So this, in this particular case, x holds, and so y has to be true sometimes in the future. So, and the y property is the pink circle. So this means that every time q1 holds, then I see that eventually, sometimes later, y holds. So when is a temporal logic formula satisfied by a state machine? So we say satisfied, a linear temporal logic formula is satisfied by a state machine if and only if, meaning definition. Every trace in that finite state machine satisfies the formula. And this is absolutely trivial definition, right? So it's very intuitive. Example. So I have this particular finite state machine that simply couldn't be. And the statement say, I want to say that globally, x implies that there is going to be y eventually. Now, is this true or not for this machine? I see someone of you says yes. Is a consensus? It is always, it is valid? Yes, looks like it. So why? Because no matter what happens, I'm in A, x is present, I go to B, and then whatever happens, I go to Y. True means I always take that transition, right? And so anytime I get an X, which I go to B, I always have to get back with an output Y. So this is always true, right? No matter which trajectory I take, this is always true. Okay, now, this is a bit trickier. Does the following hold? G, if X is true, then eventually Y is true. So is that true or not? It looks like almost the same as before, but you can prove it's false in this particular case. How? Can you give me a trajectory that will make it false?
Yeah, I mean, just stay in B.
You stay in B. Yeah. And so, but what kind of machine is this? Non-deterministic. So you have a choice, right? And so the choice is what kills you, right? Is what makes the thing not true, because I keep on staying, right? Yes?
The previous machine that you saw, isn't that satisfying an even stronger property?
Oh yeah, you can satisfy any kind of property you want. This is such a stupid machine. But the important thing is that is what we need to prove, right? So we don't have to find the largest property that the machine defines, right? So this is just to show the simplest thing possible to explain the concept. So now notice that something, yes?
So what if Y is always present? Does this property hold, or does it? So
No, because remember that this one is the actor model, right? So this is presence or absence.
Yeah, so my question is basically, does F mean it has come after? Does it have to come
After,
or
later.
It comes before and it's always there?
That's okay too.
That's also okay. So
That's
it's
also
not
okay.
a strict after. It is
No. Is that whatever? No, but important things is that from a certain point on, it's true. If it's always true, hallelujah. But it's a stronger property. Okay. Now, what is the error trace? We already say what the error trace is, and it's because of a non-deterministic choice, right? All right. Third TL operator, this is stupidest operator. It simply says that the property has to hold for the next state. Okay, right. So here it is. You say formula xp must be true in Q1, right? So the next state has to be true. That's proper. Now, the fourth operator is until. We already discussed it. This is true until something happens, and then all the bets are off, right? So it can be true, may not be true. Who gives a damn? Now phi2 takes the place of phi1. So then we have Q0, so the P1 holds, and then Q1 holds, and then Q2 holds, and then Q3, P2 holds. And now, from then on, P2 holds, and I don't give a damn about P1. That's what it is. Now, talking about what you say, if P1 continues to be true, hallelujah. Right? And in fact, there is an operator that is called weak until that does exactly that.
So this is priority, basically.
In some sense. So, well, more than priority, it says that, for example, I say I don't want to break my leg, so I'm running down the steep, and so I cannot go faster than 10 kilometers per hour, right? Until I'm flat. And then I can go 500 kilometers per hour if my legs allowed that, right? So that's until 10 kilometers. After that, go to whatever speed you want, right? Because it's true that I'm flat. So I may not be able, given my speed, I probably, I can go faster than 10 kilometers per hour. But the point is that I may be impeded to go 10 kilometers because I'm old, and so I get there, and I'm flat. I could go faster, but I keep going 10 kilometers. So which is certainly satisfying, right? But I don't care. Right? Okay, we continue. There you go. Okay. In which, does not require P2 to eventually all this variant does. Okay. So remember, so GFP means that globally, eventually P is true, right? And FGP, eventually, globally, P is true, and so on. All the kind of combination you can dream of, right? So you can mix and match whatever you want. All the formula is okay, because that is the standard rules according to which you build a logic that says that any nesting of the basic operators has to belong to the space where you started from. So any composition of this belongs to the space of linear temporal logic. Okay, so we already say P holds infinitely often, GFP. FGP, eventually P holds henceforth. GP implies FQ, and every P is eventually followed by a Q. And this one, FP, implies XXQ. If P occurs, then on some occurrences, it is followed by a Q2 reaction later. So I have to use XX. And so, okay, one step, two steps. Yes?
Does the X property hold only on the next suffix of
Has to be. Next state. But if it is true from then on,
it
doesn't matter. Okay, so the statement is about the next state. The next state. Okay. Whenever the iRobot is at the ramp edge, cliff, eventually it moves 5 centimeters away from the cliff. So the P properties, iRobot is at the cliff, and the Q iRobot is 5 centimeters away from the cliff. Now, that is some properties that your solutions for the iRobot to move up and then down has to satisfy. Okay. Now, whenever the distance between cars is less than 2 meters, then the cruise control is deactivated. Well, actually now, you have what is called adaptive cruise control. And what happens is that you adapt to the speed of the guy in front of you. So you can still go in cruise control. It maintains the safety distance, and you don't have to mess around with the cruise control. Okay? So, but this is another example. Temporal operators and relationship. So G, F, X, and U, all of them express properties along system traces. And then the question, as I said before, what is the basic number of operators that you need to be able to express every other operator? And so can you express F in terms of U? What about X in terms of G, F, or U? And so this is an exercise. The answer is yes. Okay, except for the last one. The last one ain't true. So, for example, can you express GP purely in terms of F? As we already said, right? G of phi means that F of not phi is never true, which means that eventually I never have phi, which means that globally I have phi. How about f in terms of u? We can say f of phi is true until phi, right? True is always true, so it's obviously, you obviously can do that, but this cannot be done. Okay, so the basic operators seem to be f and u, right? So with f and u and x, I can build G. Right? Some points to ponder. So a mathematical specification all include properties that the system must or must not have. So the point is that there must be some human that says that this is a correct property to assert. So the bad stuff is always at the beginning, so the origin of everything. Are we sure that what we specified is correct? For example, hold on to your seat, because in some of the standards that you have around, you can prove that the specifications are inconsistent. Which means that if you apply a logic formula for all the statements, you get a false state. So it can never be true. And so how come then, for example, the specification 100 plus pages, big volume of the Pi bus. So the Pi bus, one of the many buses that is used inside a laptop or a computer, right? Now, in that, we try to codify all these things, and after 20 pages, we already found 10 inconsistencies, and then we'll let it go, right? And then you say, well, but that is a standard, right? And so people build against that standard. You know how it's done? There must be something that people compare against. And so what they do is that there is someone in the standard committee that gives you what is called a reference design. And this reference design is say if this one satisfies the requirements. Of course it cannot be, right? Because the requirements are inconsistent. But someone has said, well, this is the best I can do, and this is good enough, right? And so everybody else checks if he is compliant to the standard with respect to the reference design. End of story. So they don't give a damn about the inconsistency, which I would not follow if we are talking about safety critical system. So if my specification that I shall not die if I put my pacemaker, I want that to be true, right? And not say, well, okay, this is a reference, this has not killed anybody so far. Okay, am I good enough with that statement? No. So that is the difference. So, in fact, there is a market, if you like, for things that check the consistencies of the requirements. So you can say, is everything that I wrote, kind of clashing, right? So, like, I want the cake and eat it too. In Italy we say you want to have your companion drunken and your bottle of wine full, right? And that's kind of contradiction, right? So the point is, how do you check that kind of contradiction? You can do that, right? So there are programs that do that. And so you run this test to see if you have not said something obviously stupid. So that's analysis of the requirements. So requirement analysis. Fine, so assume that you have this wonderful tool and that you can indeed check all the requirements, which implies that all the requirements can be written in temporal logic or some other logic, because otherwise how can you do that? But am I satisfied enough of my set of requirements or not? So all what I've written doesn't clash, so it's consistent. Okay, good. Is this a necessary, sufficient condition to be satisfied with what I've done? Or is that necessary? Necessary for sure, right? Yeah, so it's consistent. But is that enough? Now, what is complete? The other thing is completeness. Who tells me that I put down all the requirements? Now, who can do that? No, God in person, right? Because where do we compare against? Right? And that is the biggest problem of requirement engineering, is to be sure that you express all what you wanted your design to have. So sometimes you have a wrong design and you have disasters because you forgot some conditions. And this is, for example, for the side effects, right, of things that kind of happen that you never thought could happen. Right? So in fact, there are tools that tells you that explore the space, which means they try to poke at a combination of variables that you have said nothing about, right? And then they come to you and say, look, if you set these variables to this value, the following happens. Are you sure you don't want to say anything about it? And this is called requirement space exploration, right? So, but this is still, you can never be sure, right? So, and this, unfortunately, unless we are God, we can't solve, right? The initial step is always very difficult. But if we have everything okay, I feel pretty good. Okay. Now, getting the specification right is often as hard as doing the design. My own opinion is that in the end, we're going to do everything by synthesis, right? If we do all these steps, right? And as I said before, like platform-based design and all that, everything can be done automatically, but the original specification. So the original specification is the design. In the end, 20 years from now, that will be the design. Is writing down the specification. Okay. So interesting research direction are inferring temporal logic for system traces. So in this particular case, I say, okay, this system is correct. Now, can I see what kind of properties this system has got that I can abstract? This is similar to the question that he asked before. And I say, well, gee, that small machine had satisfy even stronger conditions. And I said, but in this particular case, it's a reverse problem, right? Which is this one. So can we build the set of all properties that a particular design that I give you through a set of traces satisfy? Okay? So that's the inferring temporal logic from system traces. And then the other thing is that, remember what I said, that everybody does and that everybody uses doors? I mean, when I say everybody, it means everybody in the world. But that is English, right? So natural language. Now, can we try to extract from the natural language what these Turkeys have written, some kind of mathematics? Now, if that is the case, then it's great, because in general, system designers are not expert in temporal logic, and I don't blame them, right? There are all kinds of gray nuances in there. And the gray nuances is that you constrain the natural language in such a way that you have a formula sitting behind. That's called pattern-based specification capture system. Pattern-based means you can say the following word, but don't use other words, right? So the English, you can only use words in this sequence and words in these combinations, right? And then I can build a logic temporal, a linear temporal logic or a computational tree logic or whatever other logic you want behind the scene. So you can see when you say things, you're still intuitive, but I can build the thing behind it. Right now, this is a boundary. This is the place where, for example, we work with IBM. IBM is the guys who have doors, and they would love to have such a system, of course, because all of a sudden they can sell more simulation tools, they can do better design, everybody's happier, right? So that would tell you that even at an undergraduate level, you can still kind of formulate very modern research problems that have so big impact in the domain. So this is specification mining. So you got a horrible system like that, and then you check it out, and you find out that all the trajectory of that system satisfy the following property, that the settlement time is 7.25 milliseconds, and the overshoot is 100 units, which means that all the possible trajectories that I am getting out of that system satisfy these two properties. So it must be that this is the property that if I do redesign of that system, I must assert. Okay, so that's a specification mine. Now, the space wire specs is the Turkey protocol that we showed before, is that the reset state, right? What happens when something goes wrong and where you have to go, etc. So you can write in temporal logic those specs, and also you can also write in temporal logic the iRobot specification. That would be interesting because you could do then in the lab try to see whether your implementation of the control satisfy what the design is supposed to be. Okay, that's it. That's the end of class for today. And we are 10 minutes early, so questions of any kind and sort about soccer games? I can answer that too. Probably better.